Suppose you play a certain game 20 times. Each time you play, you can either win or lose. There's no such thing as a tie here. We know that the probability that you win any one game is 55%, and the probability that you lose is 45%. We might think this is a binomial experiment, so if that's a suspicion, we should check it. There's three things that must be true in order for this to be a binomial experiment. One, we need to make sure that there's a fixed number of trials. In this case, we're playing the game 20 times, so we have a fixed number of trials. We have 20 trials. We need to also check that there's exactly two outcomes, no more, no less. We usually call these outcomes success and failure. In this case, we're calling them winning and losing. We have exactly two outcomes. Last, we need to make sure that the trials are independent. We're playing this game 20 times. Games typically begin and end, full wrap-up, so one game is not going to impact the results of the next game. So these games are independent, and you can assume that unless there's something stating that they are not independent. So in this case, nothing implies otherwise, so yes, our trials are independent. Because we're able to confirm that this example is a binomial experiment, we know that the outcomes of these games, the number of times you win out of the 20 trials, it follows a binomial PDF. That's a binomial probability distribution function. To compute the probability for any outcome, say we want to know what the probability is that we win 8 of the 20 games. We first need to identify some values. One, the number of trials. We have 20 trials, so n is 20. The probability of success. We know that we have 55% chance of winning any game, so our probability of success is 0.55. We use the letter p, a lowercase p, to represent the probability of success. And then lastly, Q. Sometimes you're given Q and sometimes you have to find Q using P. Q is the probability that you fail, or in this case, that you lose the game. We know that winning and losing together makes up 100% of the possible outcomes, and so we can use that idea to calculate Q using 1 minus P, or 1 minus 0.55, which gives us 45%. And that's actually given to us in this example, but if it wasn't, we could have calculated it ourselves. The binomial distribution function is a pretty complicated looking formula, but we're going to use our calculators to do this for us, so we don't need to get too detailed on using this formula. But basically, we would plug in 20 for our combinations, we would plug in 0.55 in our P, and we'd plug in 0.45 for our Q, and then lastly a 20 in this exponent. Since we're going to use our calculator, I'm just going to jump right to the table and a graphic to represent all of the possible outcomes from this probability distribution function. We have a bar graph that represents each of the probabilities of winning a certain number of games out of the 20 trials. We have the same information displayed in a table. Whether we're looking at the graphic or the table, we can find information like what's the probability of winning 8 games out of the 20 times that we play. In the graphic, we're just looking for the bar above the x equals 8 and reading how tall it is. In the table, we're looking for the x equals 8 in the first column, and then reading in that row what the probability value is. So either way, we get the same result. We just read them differently. The probability of winning 9 games, the probability of winning 10 games. In fact, we can do this for any number of games, 0 through 20. We could lose every single game, so win no games, or we could win some games, lose some games, or maybe we win all 20 games. With a binomial experiment, we can use a random variable that represents the number of successes out of a certain number of trials. So if we let our random variable, x, be the number of successes out of the 20 trials, we can answer questions like, what's the probability that you win 15 of the 20 games? Well, in our mathematical notation, that would look like p parentheses x equals 15. And we can read that either by reading the height of the bar in the bar graph or reading the appropriate value from our table. We can see that there is about a 4% chance that we win 15 of these 20 games. What about the probability that you win fewer than 5 games? Well, fewer than 5 games, looking at our table, would be winning 0, 1, 2, 3, or 4 games. We wouldn't include 5 here because 5 is not fewer than 5. So maybe instead we want to write our notation as the probability that x is less than or equal to 4. That way it's clear that we're not including the probability of winning 5 games in this calculation. Since we're talking about a range of values for our variable, we're going to need to combine the probabilities for x equals 0 through x equals 4. Now, the probability of winning 0 games is very small. Same with 1 and 2. They look like they're 0 right now, but that's technically a numerical 0. There's a very, very, very tiny chance that you win 0 games. But anyways, when we combine the probabilities from rows 0 through 4, we get a combined probability of almost 0.15%, so a very small chance of winning 4 or fewer games. What's the probability that you win more than 5 games? This is another one that we need to be careful about. More than 5 does not include winning 5 games, so that would be 6 or more games. We could add up all the heights of the bars for 6 and above, or we could add up the numbers from the table. Both communicate the same results, and when we combine all of the probabilities for 6 through 20, we get a probability of about 99%. So there's a very strong chance that we win more than 5 games.